Well, good afternoon. It's 2:31, 1 minute late getting started on Wednesday, the 19th of February, 2020. It's supposed to be differential equations class, but the trouble is I'm the only one in the room at the moment. Hopefully the others will be coming. Let's go on and get started from where we left off last time. I'll wait and do announcements when I get an actual body in the room. So, we're in Chapter 2, First Order Differential Equations, Section 2.3, which involves linear equations, and we're on near the bottom of page 59, which is, we're starting a little section called Piecewise Linear Differential Equations. Now, I'm going to read the first part because I hope it'll give some sort of justification for why you'd ever do these. But here it is. In the construction of mathematical models, especially in the biological sciences and engineering, it can happen that one or more coefficients in a differential equation is a piecewise defined function. In particular, when either the p of x, which is the coefficient of your y term, or the f of x, which is the term on the right side of your equation, is a piecewise defined function, then the equation is referred to as a piecewise linear differential equation. In the next example, f of x, the right-hand side, is a piecewise continuous, on the interval from 0 to positive infinity, with a jump discontinuity at x equal 1. Okay? So that means it's piecewise continuous meaning for the various pieces. I just don't really like the wording of this, but okay, but I still don't like the wording of it. It's not what I call a jump discontinuity. I would call this a replaceable discontinuity at x equal 1. The basic idea is to solve the initial value problem in two parts corresponding to the two intervals on which f of x is defined. Each part consists of a linear equation solvable by the method that we've been talking about. As we'll see that it's possible to piece the two solutions together at x equal 1, then so that y of x will be continuous on 0 to infinity. Okay. The verbiage is not all that great, but let's proceed with it and see what's happening. Here's example 6, bottom of page 59. We'll go on to page 60. Here's the differential equation. Let me get my pen set up. Okay. dy dx, that's the ugly d, plus y is equal to f of x. A classic, simple, linear differential equation. Okay? Here's the initial value. Y at 0 is equal to 0. Okay? Where your f of x is equal to, here are the two pieces, 1 for any time 0 less than or equal to x is less than or equal to 1. Okay, in other words, the right-hand side is equal to 1 between 0 and 1, including 0 and 1. But it's 0 anywhere x is greater than 1. Okay, and that is indeed a jump discontinuity at x equal 1. Constant function of 1 between 0 and 1, and then 0 from there on out. Jump discontinuity. All right. So what we do is solve both differential equations. So the first one would be this: dy dx plus y is equal to 1. Well, this will only be good for 0 less than or equal to x is less than or equal to 1. Now, here's what I want to say at this point. I know it's too early to say it. This seems like this should do everything we need because your initial value is at x equals 0. That's all we need, okay? But anyway, obviously it's not. We need to do something else. So how do we proceed? First, identify your p of x. Your p of x is equal to 1. Okay? And what you do with that? You e it, okay? I'm sorry, you integrate it. Sorry, I'm e-ing too fast. Okay, you integrate that dx. Okay, so integral of dx is equal to x. Then what you do with that? There you eat it. Okay, and that becomes your integrating factor. So then you multiply that by everything on both sides. E to the x dx dy dx plus e to the xy is equal to e to the x. All right. As a student. He's here. All right. I'm going to pause just a moment here in my talking to turn on the projector and flip the lights. And give this announcement. I think you heard it last time, but just in case you thought of anyone or anything else, I'll do it again. We have here at the college, a workforce development area, okay? And for companies, businesses, whatever, they may sometimes come in and ask for training that we can provide. And obviously, Alabama Power and some other utility and contracting companies have come to the college and said, look, we need some more line workers trained. Can you do it? And we've said yes. Now here's the bad news on it. The applications are being accepted through today only. Okay, so if you know of anyone who might have any inkling of wanting to do something like this, let them know today. Okay, today is the last day they can do it. The training won't begin until June the 8th, and it lasts till August 14th. It'll meet Monday through Friday, 8 to 4, for those 9 weeks. I'm sure there'll be a lunch in there somewhere, probably an hour for lunch somewhere in that time frame. The program tuition is $4,150 plus the fees. The fees will include your books, the PPE. Now I found out what those were. Personal protective equipment, okay? Which you either probably have to buy or rent. I imagine you probably can rent it if you need to just for the training. There's also, part of the course is a commercial driver's license, and you have to have a physical before you can get that, so you have to pay for your physical. There's also various permits, licensing, and exam fees, depending on what kind of certification you're planning to get at the end. But that sounds like it might be a lot, but scholarships are available. Evidently, the companies are really in need of line workers, and someone has come up with some scholarship money. So what are the program outcomes from this? When you finish this program, you'll be OSHA 10 certified. Now, I don't know exactly what that means, but it sounds pretty impressive. OSHA is Occupational Safety and Health Administration, and you'll have their OSHA 10 certification. You'll also have your commercial driver's license, which is valuable in itself. You'll also have been trained in cardiopulmonary resuscitation, CPR training. So that's valuable in itself. And of course, you will have your basic line portrait skills. So if you need more information, but you don't have much time to get it, but if you need more information, our Office of Workforce Development, Mr. James Gray, Dr. James Gray, is the Workforce Development Manager, and I have his phone number here, I have his email address. I'm pretty sure he's located right across the way in either Ethel Hall building, which is one you see, or the one on the other side of Ethel Hall, which has the slanted roof. That is a Jesslanier building. So they're almost adjacent. They're connected by a walkway. They're right next to each other. So either one of those two buildings, I think, is where he's located. If he's not in one of those two, he's probably over here in Millsouth, but I believe it's one of those two buildings. I have his email address and phone number. And you can contact Mr. Tommy Hobbs, Assistant Dean for Workforce Development. Now, in order to apply, you have to go to a website, a link. Okay, I have the link here. It's an Eventbrite site, and the title of it is Pre-Apprentice Power Line Worker Application Tickets. And then there's other numbers and other things in it. But that's where you have to go to apply, so you need to do it before the end. Don't know if it's the end of business today, end of the day, something like that. You have to. And that's last time you hear it, because it's going to be gone by the time you get back. Now, one other thing, I can't remember if I said this one on Monday or not. Normally I have office hours on Friday mornings from 8 to 12. On the Birmingham West Campus. Not this Friday. This Friday, I've been assigned to go to Opelika, to Southern Union Community College, and there work on a state team doing revisions of some of our course descriptors and things like that. And the meeting goes from 9 till 2. But to travel from here to Opelika is going to be close to 3 hours. So we'll be leaving sometime around 6-ish in the morning from the Birmingham West Campus. So I'll be on campus, but it'll only be a little around 6 o'clock, and then we'll be leaving. And then we won't be getting back probably until around 5 o'clock. And so I'll be back on campus again, but that's going to be awfully late in the day, and I'll just be there to... If you want to catch me either of those times, that's the only time I'll be on Birmingham West Campus Friday. Now, in addition to that, the odds are, I haven't gotten permission for this yet, but I hope to get it by Friday. I may take off the following Friday, because normally I work 4 hours on Friday. That Friday is going to be 6 to 5, which is 11 hours. I hope I can take this next Friday off, because I will have put in more than 2 Fridays worth of time on that Friday. So I would otherwise have to take personal leave. Hopefully I can take comp time for that. So anyway, that's coming up. That's the only other announcement I know of. All right, now I had already started on example 6, bottom of page 59. This is a piecewise defined function. Define differential equation. The differential equation is dy dx plus y is equal to f of x. Standard linear differential equation. It's an initial value problem. Y of 0 is equal to 0. But what's different about this is f of x is a piecewise defined function. Now they said you could also have p of x being a piecewise defined function. That's going to take a little different approach, but the f of x is pretty easy, and what this one is f of x is 1 anytime x is between 0 and 1, and it's 0 anytime x is greater than 1. So this function is defined only for x's greater than or equal to 0, and there's a jump discontinuity at x equals 1. So what we're going to do here is first do it with the first part. This is dy dx plus y is equal to 1, and that's only good for 0, between 0 and 1, x equals 0 and 1. So what is your p of x here? It's the number 1. And I just was trying to indicate where to look for it, and it came out looking like a 0. So I'm going to erase that 0 so you won't get confused by that. And so the p of x is 1. So you integrate that p of x, integral of dx is x. Then you raise that to the e. That becomes your integrating factor. That's where I left off. So multiply that by every term on all terms in your differential equation. E to the x dy dx plus e to the xy equal e to the x, because this is when you're equal to 1. Okay? Now, hopefully, and we'll verify this, the left-hand side here should be the perfect derivative of e to the x, your integrating factor, times y. Let's see if that's the case. The derivative of a product is the first times the derivative of the second. That's exactly what we've got here, plus the second times the derivative of the first, and that's exactly what we've got there. And that's equal to e to the x. Now, I didn't put my dx in the bottom because I'm going to put it over here. Okay? And then I'm going to integrate both sides. And this is just going to, the integral of a derivative, a perfect derivative, is e to the x y. And that's equal to antiderivative of e to the x is e to the x plus some constant c. Okay? We're going to evaluate that with our initial value. Okay? But first we're going to divide everything by e to the x. And that would then produce y is equal to 1 plus c e to the minus x. Okay? And evaluate that at x equals 0. You get 0 is equal to 1 plus c. So c has to equal -1. Okay? So our function now is y is equal to 1 minus e to the minus x. Okay. That's anytime x is between 0 to 1, there's your solution. Okay. Now, I described earlier, though I didn't draw it, but I'll let you see the drawing of it. Here is your f of x at the end. It's 1 from 0 to 1, and then 0 from there on. Okay? And we've dealt with that. Now, this is only good from 0 to 1. This solution is only good between 0 and 1. Okay? Right here. What about for x is greater than 1? Well, then we have to plug in the f of x equals 0. So dy dx plus y is equal to 0. Well, still your p of x is 1, and the integral of that is x. You take the e of it, your integrating factor is e. So the only difference is e to the x dy dx. All right, that's perfect attendance today. That reminds me. I should have done this earlier. They have dropped Gunter, Peyton Gunner from the class, so that means I can't put him back.
I saw you posted it.
Y'all both did quite well. Okay. As expected. Okay.
Question.
Yeah.
You got a lot going on in this last segment. Do you still have the letter that you wrote me for the? Basically, I'm just doing this internship application and maybe a couple of recommendations.
Okay. Did you send me information about what to do on it?
On That one, I think that was for the STEM program, and I think this one they just want, let me see, exactly.
See, I was afraid I missed your email, if you sent me an email on it.
I didn't send you one this time. It just says, please have 2 people familiar with your academic accomplishments and levels of reference.
Okay. Say that one more time.
It just says, it doesn't say anything else like criteria wise, it just says, please have 2 people familiar with your academic accomplishments and levels of reference.
So it's letters of reference. Okay, what is it you're applying for?
So this is one for UAB, but it's just an internship for like a lab internship.
Okay, it's not.
Yeah, it is.
It's not one of the REUs?
Not that I know.
Okay. Okay, when do you need it?
Hopefully tomorrow.
Okay. I'll try to get it
And
done.
I'll come pick it up from you wherever you come to campus.
I'll be on this campus tomorrow. Normally I'd say I do it on Friday, but I'm going to be traveling to Opelika on Friday. So I'll try to get it done before. Okay, now the other thing that you mentioned, the STEM program. I can't remember. Did I do that one?
Yeah, you did that one. You did that one.
Okay.
And you gave me a letter. Was that last semester? I can't remember when, but you did have one that you did do, and I didn't know if you still had that.
Okay.
That one would work for this one.
Okay. Well, what I was going to say, who do I address this to, or just leave that?
So I'm gonna put it all in the envelope and everything, like, because I got a part that I gotta do.
Right.
Put in the envelope. I'm gonna just take it to you.
Okay. So I just do it to whom it may concern, or something like that.
Yes, sir.
Okay. So I don't address it to anybody particularly.
Yes, sir.
Okay. I'll try to pull up the one that I did and take off anything that's specific to STEM program here, and just say for a lab internship. Is that what I call it?
Yeah. Well, I know I basically think they just want to know like how I perform academically.
Right. And did I address that in the letter?
Yeah, in the one that you wrote before. That one, because I remember what you wrote on there, and I think that would be like exactly what they would.
Okay. All right. But I don't address it to any
it's
group
not
or
specific.
anything else.
No, sir.
Okay. Okay. All right. I'll try to pull that up and print it off, and I'll be on campus tomorrow from 8 till 6,
Okay.
and I'll be in class almost the whole time. I'm free from 8 to 8:30, and the only other reasonable chunk of time is from 12:45 to 1:15. I mean, that just about it. Other than that, it's 15 minutes in between classes.
Okay.
And then usually right before 6, I'm ending the lab.
Would you like me to come later on that day? I don't want to like interrupt like your lunchtime or anything.
Okay, what have you got right after this? No, wait. I can't do it.
Yeah, you got it.
Oh, I got to
That's
go
what I
on
said.
the
I know
campus.
you got it.
Yeah, so I'm not going to. I got to do it in the morning between 8 and 8:30.
Okay.
Okay, so I'll try to remember to do that in the morning between 8 and 8:30. Print it off, and then what time would be good for you?
So I do work in the morning, but I get off around 11, so I could easily be here at 12. But I know you said in between that you got classes.
If I've got it done by before 8:30 in the morning, which I hope to have it done then, I'll leave it in my office, and my work study student will be there. I don't know what time she leaves, but she's usually there at 1:15 when I start my class, and she's gone by the time I'll end it at 5:45. So yeah, if you're there before 1:15, you'll either catch me or her. Okay. And so whether I'm in class or there, I should be there. Okay.
Did you need the envelope?
No, I mean, you're just going to pack it.
Yeah.
Are you supposed to see it or not see it?
They didn't say I could.
Yeah, okay.
Yeah, because I just was asking because we was located in like Boston State.
Right.
Boston
is she coordinating it?
No, it's not her. I just was asking her what they mean, like, by the application. She explained it to me.
Okay. Well, unless you want me to seal it in the envelope, I'll just give it to you and you can package it any way you want. If you want to put it in the envelope, you can. But since I don't have anyone to address it to, it seems like just a waste of an envelope. Okay. All right, I'll try to remember to do that first thing in the morning. And I was trying to remember if I had done the letter because I knew you had asked, and it just, so much is water under the bridge. I can't remember who I've done for and who I haven't. So, okay. All right. So what we've got is this is example 6, bottom of page 59, top of page 60. We're on the top of page 60 now. What it was is a differential equation, dy dx plus y is equal to f of x, sort of a standard-looking linear differential equation. And it's got an initial value, y of 0 is equal to 0. What's different about this is the f of x over here is a piecewise defined function. It's 1 between 0 and 1, and 0 anywhere past 1. Not defined for any x's less than 1. So, we do the first part of it, because that's where your initial value is, between 0 and 1, it's at 0. So we do that when f of x equals 1. We've done that one, and we came up with this differential equation. Y is equal to, and plug in the initial value, that y is equal to 1 minus e to the minus x. Okay, you can go back and listen to how we got that. Okay, now, what that has done for us is only, and this is only good between 0 and 1. This is not good past 1 because that's not your function. So what we're going to do is do the same differential equation, but now have it equal to 0. This is only going to be where x is greater than 1. Okay? So, our first part is exactly the same. Your p of x is equal to 1. The integral of p of x is equal to x. Raise that to the e, that's your integrating factor, e to the x. And now what we're just going to do is multiply that, just like we did before, e to the x dy dx plus e to the x times y, but this time it's equal to 0. And again, that is the perfect derivative of e to the x times y, so that happens just the same. If I can get my pen to write, and it's not writing, I don't know what's going on with it. There it goes, okay. D of e to the xy, but this time this is equal to 0, okay? So you get e to the x times y is equal to some constant, because the antiderivative of 0 is a constant, okay? So your y here is equal to e. Now this is not the same c as we had before, so I should have fixed that a little bit, chosen a different one, but we've already done that c. So this is c e to the minus x. Okay. Now, this is the kind of the strange part. This function here is a jump discontinuity. It's 1 between 0 and 1, 0 everywhere else. The function we've got here is a function that at x equals 0, you're at c, you're at 1, okay, because, no, you're at 0, aren't you? Because when x is equal to 0, this is e to, this is 1, okay, 1 over 1, that's 1, 1 minus 1 is 0, so you're at 0. But you're going up a curve sort of like this until when you get to x equal 1, which is the only place it would be good, this is 1 minus e to the minus 1, that's 1 over e, that's about 1/3. So this is something a little bit greater than 2/3. So you've gone up to around 2/3, but now you've got to connect to this. Because even though that's a discontinuity, it would be better if your function was connected there. So what are we going to put in there for our c? Well, what I would suggest is figure out what, and we just did, when x is equal to 1, y at 1 is equal to 1 minus 1 over e, right? E to the minus 1. And that is the same as e minus 1 over e, okay? So, let's make that a requirement here, that y of 1 is equal to this. So this will be e minus 1 over e is equal to c over e. Well, that means that c here, this is a different c now, is equal to e minus 1. That's not a superscript, that is same line, e minus 1. Okay, so let's plug that in, and we have, so this is the function, but when 0 less than or equal to x is less than or equal to 1, and this one will be y is equal to e minus 1 times e to the minus x. And this will be anytime x is greater than 1. Well, is there anything we can do to make that a little smoother? I don't know. You could say this is e to the 1 minus x minus e to the minus x. I don't know if that's any clearer or not, but that's another way to write it. So, they didn't. They just left it just like we did. So your function, and here's how they summarize it. Y of x is equal to piecewise function, but this is a continuous function. 1 minus e to the minus x anytime x is between 0 and 1 inclusive, and e minus 1 times e to the minus x anytime x is greater than 1. Okay? And if you plug in x equal 1, you see those will have the same value there. Okay? Right. Okay. And that now is continuous everywhere from 0 to infinity. Okay? Now, whereas this was your jump discontinuity of f of x, that's the right-hand side of your differential equation, here is what your solution for your differential equation is. It's a exponential curve going up, and then it is continuous, but now it's a decaying exponential function in this direction going down. Okay? This would be a decaying exponential function, but it's 1 minus that, so that means you're going up until you get to 1, and then from there on you're going down. Okay. Now, they talk about this, goes on to example problem 53 at the end of this section. We'll get there when we get there. The next thing they're covering here, any questions on this? I know that was sort of a complicated problem, but it was You just take it a piece at a time, and none of the pieces were that difficult. Maybe following my board isn't difficult, but the pieces themselves weren't that bad. All right, so let's clear this unless there are questions. All right, the error function. That sounds like a negative thing, doesn't it? The error function. You obviously made some error somewhere. No, in mathematics, science, and engineering, some important functions are defined not in terms of y is some function of x, okay? They're defined in terms of non-elementary integrals that you can't solve by themselves, okay? Two such special functions are called the error function and the complementary error function. And here's what the error function is. ERF, that stands for error function, of x. Most functions have a one-letter name. This one has three. Error function, okay? ERF of x is equal to, strange-looking coefficient, 2 over the square root of pi. Who would have thunk it? But here is the part that's even worse. You have an integral that defines this function, 0 to x. There's your variable, x, e to the minus, and it doesn't matter what you call this. Most of the time they do call it t squared dt, but that's just a dummy variable. You could call it s squared ds, you could call it phi squared d phi, you could call it anything except x. X is not a good thing to call it because x is your variable that's at the top of the evaluation. This is just a dummy variable, meaning you proceed from here. Now, that integral is not solvable. It's called non-elementary. You can't solve it. There's no y is some function of x or function of t or anything else that's going to solve that. Okay. Now, the second is, very similar to it. This is the ERFC, the complementary error function. Okay. Complementary, now that's not, you're paying it a compliment. This is the completing function, error function. And that is the same strange coefficient, 2 over the square root of pi. The integral starts looking the same, except this goes from x to positive infinity. Okay? An indefinite integral at best, e to the minus t squared dt. The rest of it looks just the same. Okay? Though that's your complementary error function. Sorry about this. All right. Now, you can go to Appendix A and see this proven if you want to. They just say, from the known result, and here's what they're saying, the integral of, from 0 to infinity, of your error function e to the minus t squared dt, okay, is equal to the square root of pi over 2. All right. Now they put an asterisk here and say you can go to the integral and see that. That's what they say they know. So what they do is divide both sides by the square root of pi over 2, which is the same as multiplying by 2 over the square root of pi. And this is going to be 0, because that over itself is going, I mean, not 0, 1, because a number over itself, root pi over 2, divided by root pi over 2 is 1. Sorry. And that's why then, since this is 1, this integral right here is 1, then you say split this into two pieces, the first piece being 2 over root pi of the integral of 0 to x, okay, e to the minus t squared dt, okay, plus the complementary piece, which is 2 over root pi times the integral from x to infinity. See, basically what you've done is split this integral, 0 to pi, that we know that's equal to 1, okay, into 0 to x, and x to infinity. But these two added together has to equal 1, okay? So that would be e to the minus t squared dt is equal to 1, because it's equal to 1 up here. We've split it into the two pieces. So that's why they're called complementary. This one completes that one, this one completes that one. They complete each other to make a total of 1. All right. This perhaps sounds like gobbledygook, okay? Maybe. But think of this, the bell curve. Probability under the bell curve is supposed to be 1, okay? That's what this is saying right there. The probability of being in something is 1, and if you're in this side of it, you're 1 minus that side of it. Total probability under the curve from 0 to 1 is 1, so you're either in this part or that part. If you're in this part, that's going to have to be less than or equal to 1. Otherwise, because these are both positive, values, e to the minus anything. The e function is always positive. So this is basically saying you're either on this side or that side of it. But the total of it is 1. Okay. So basically what this is leading to is what I just said. The error function as a function of x plus the error function complement as a function of x, that's equal to 1. And because of its importance in probability, statistics, applied partial differential equations, the error function has been extensively tabulated, and you can go to lots of statistics books or anywhere else and find that done. All right. Now, top of page 61, if we're solving an initial value problem, similar to what we have done earlier, and recognize that indefinite integration of the right-hand side would lead to a non-elementary integral, I can't get the word out, then it's convenient instead to use the definite integration over some finite part of it and then go from there. The last example here illustrates this procedure. Automatically incorporates the initial condition at x0 into the solution for the differential equation. In other words, we do not have to solve for the constant in the general solution, blah, blah, blah. Okay, so let's deal with one. We know already where it's going to turn out, something to do with the error function. So here's the initial value problem. dy dx minus 2xy is equal to 2, and y of 0 is equal to 1. Okay, that's the initial value. I hope you can read my writing. It's pretty sloppy. Okay. That differential equation is in standard form, linear standard form. No way we can separate variables because of that 2 at the end. If there'd been a 0 out there, yes we could. Can't with the 2 there. So, where do we begin? Where do we begin? The p of x. P of x is equal to minus 2x. Okay? Now the integral of p of x dx would be the integral 2 times negative 2 times the integral of 2x dx. Okay, sorry. Developed a twitch in my eye, and it's hard to focus. Okay. There is our integral of p of x dx. Okay. And what does that come out to be? Minus x squared. Is that what you said? We don't ever do a plus c on this one. Okay, just minus x squared. What do we do with that? Raise it as the argument of e. That becomes our integrating factor. Okay, what do we do with that? Multiply by everything in your differential equation. That's e to the minus x squared dy dx minus 2xy e to the minus x squared. I probably could have written that first, but and that's equal to 2 e to the minus x y x. What am I doing? Okay. Minus x squared. xy was over here, x squared. Okay. I think I got it right that time. Okay. Now, supposedly, this side should be the perfect derivative of the integrating factor e to the minus x squared times y. Let's see if it is. Okay. When you're doing the derivative of a product, it's the first times the derivative of the second. That part's perfect. Okay. Plus the second, y is there, times the derivative of the first. So the derivative of this is e to the minus x squared. Chain rule times the negative 2x. Negative 2x e to the minus x squared dy, y. It's the derivative of this, which is e to the minus x squared times the minus 2x. Okay? Yeah. Because the derivative of this is minus 2x e to the minus x squared and then times y. The function there. Okay. So that worked. And this is equal to 2 e to the minus x squared. Okay? When you integrate that, okay, this gives you e to the minus x squared y is equal to 2 And here's your error function. The integral and we'll call this 0 to x e to the minus t squared dt. Okay. Multiply both sides by e to the x squared, and you get y is equal to 2e to the x squared. Okay. E to the x squared times your ERF. I think that's adequate. Just no, not quite. We're not quite there yet. Okay. I was trying to jump a gun here. Let's do what we had down here. Integral from 0 to x e to the minus x minus t squared dt. Okay. Okay. I haven't put my c in there. I'm missing my constant. I don't see where they did it. I know they had to have done it. They what? Yeah. Yeah, but I mean, okay, but they gave us an initial value, and we need to plug it in somewhere, and
well, that's what I was saying. Like, they use the initial value for the units of integration. Like, this initial base value is 0.
right.
Just ran from 0 to someone.
So right down there is where it's the
Yeah, that's the initial.
yeah.
Just because, like they saying that the reason why they did that is because it's not so
Yeah. We identify x of 0 equals 0 and use a definite integration of that. Okay. Yeah. All right. And so basically, yeah, they basically, when they got to this part here, they got to that part there, and here's where they put in a minus y of 0, okay? And that then enabled them to put 0 to x there, because this had no limits, and that one, it looks an awful lot like a sleight of hand, but it's legal, okay? So when you do that, and your y of 0 is equal to 1, so that's why here you would have had e to the minus x, I'll write it out, e to the minus x squared y minus 1 is equal to that. Add 1 to both sides, you get e to the minus x squared y is equal to 1 plus e to, okay. Okay. Hold back just a minute. I shouldn't have put that in yet. I had done it earlier thinking it was there, but this is just a 2 here now, okay, from right here. 1 plus, no, wrong key, okay. 1 plus 2 integral 0 to x e to the minus t squared dt, okay? And then is when they multiply by e to the x squared. So that gave you y is equal to e to the x squared plus 2e to the x squared times the integral 0 to x e to the minus t squared dt. Okay. Yeah. That's their equation 14. And then, lo and behold, they interject the root pi over root pi. They put a root pi in front of this and behind it. Okay, this part here gives you the error function, okay, and the other part, you just get the root pi times the error function, okay, which is enough to drive you nuts. So the final solution is y is equal to e to the x squared, because you had that term here and here, so factor that out of there, times 1, that's when you factor it out of here, plus root pi, okay, and then everything else you got here is the error function. Okay, so you don't have to haul around all that writing anymore, because the 2 over root pi, you pulled this out, times that, that is your error function. Okay. Yeah. Okay, then there's a thing about use of computers. They talk about Mathematica or Maple. If you have either one of those, please do it, use it. The remarks at the end, I usually don't want to waste too much time on those, but they do have a couple of comments here that you might find useful in engineering lately. In further discussion, future discussions, the word input and output will occasionally pop up. The function f, that is your right-hand side, in this problem it was 2, okay? But whatever that function f is called the input or driving function, and the solution, y, of the differential equation for that given input is called the output or response function. So this would be our output function. They also have the term special functions mentioned in conjunction with the error function. Applies to, here's 2 more, the sine integral function and the Fresnel sine integral function. You will occasionally run into them, but my guess, that's going to be more in a math class than it is in an engineering class. Though, you might run into it sometimes, sine integral function or Fresnel sine integral function. And they talk about those later on. You'll see them in the problem set. So, homework exercises here would be any of the odds that you can find in the back of the book from 1 to 23. Okay? Any of the odds 25 to 35 that you can find in the back of the book. Either 37 or 39 that you find in the back of the book. 41 if it's in the back. 43 if it's in the back. And 45 if it's in the back. 47 then tells you what that sine integral function is, and if you need to know it, the Fresnel sine integral function is 48. But I wouldn't go there unless you need it. And then it's another one of these non-elementary functions. The discussion problems usually aren't in the back. If you find any that are, you can go on and attempt them, but most of the time they're not. Okay, so that finishes linear. Boy, it ended on a bad bang there, didn't we? But most of the time you'll be using what we did earlier. But we were using the same thing here to get to it, but we're winding up with integrals. All right, so let's erase this. We're going now to exact equations. Now I'm guessing we have about 10 to 15 minutes left. Second? 12 minutes, okay. I knew it was somewhere in that time frame. So let's introduce what we mean by an exact equation. Before we do, here's another way to write a differential equation. Y dx plus x dy is equal to 0. Okay? That's a first order differential equation, but it's written in differential form. Now this is one that can be, it's separable and it's linear, okay? But there's another way we can do it, okay? Now where this comes from is, if you think about it, is d of xy, okay, in differential form. That would be the second time derivative of the first, y dx, plus the first time derivative of the second, x dy, okay? Now, if that's just your product rule in differential form, okay? So in this section, so in other words, here is your function f of xy, okay? Is that x times y, and this will give you that. In this section, we'll examine first order equations written in differential form, and here is generally how they're going to be. M of xy, not just a function of y anymore, dx plus some n of xy, not just the x anymore, dy, is equal to 0. Now, just about always, these are going to be equal to 0. I'm trying to think if there's any time when they're not. I don't think there are. Okay? Now, here's going to be our approach. We're going to do a test of m and n to see if this is what we call an exact differential. First thing we're going to do is see if it is an exact differential. If it is an exact differential, then we're going to proceed with an illustration of how to solve it. If it's not, later on in the section, we're going to see if we can modify it some way to make it an exact differential. Okay? Now, there's a lot of ifs there. There's a lot of, yeah, here's what we're going to do. Okay? We left a lot of wiggle room here. Okay? Now, Have both of you had Cal 3? Good, okay. Last time I taught this course, some of the people in the course were in Cal 3, and we hadn't gotten to partial derivatives by the time we got here in this course. You need to know how to do a partial derivative. So I had to stop and do a quick course on partial derivatives, okay? So here's what we're going to do. I think I'm going to start afresh. Now, here's what we're going to start with. If you've got some function, z is equal to f of xy, okay? Some function z, a function of x and y, okay? And you have continuous first partial derivatives in some region R of the xy plane, okay? Then we can say the differential here, dz, differential z, is the partial of f with respect to x times dx plus the partial of f with respect to y dy. Okay? What that's saying is, you have z that's a function of both x and y. You can do the differential as opposed to the derivative. The differential of z, okay, would be the partial of f with respect to x. So this is a function of two variables. And then that's times dx plus the partial of f with respect to y dy. That's splitting up the z into the change of f with respect to x dx, change of f with respect to y dy. That gives you the total change of z. Okay? Sort of the quick and dirty of it. Okay. Now, here comes the special case. In the special case where your f of xy happens to be equal, not 0, some constant, okay? Where f of xy is just a constant, okay? The special case where f of xy is a constant, then the derivative of z is 0. So then you have partial of f with respect to x dx plus partial of f with respect to y dy is equal to 0, because dz would be 0. Okay. In other words, given a one-parameter family of functions, f of x, y is equal to c, one-parameter family of functions, we can generate a first-order differential equation by computing the differential of both sides of the equality. Okay? So, here is an example. Okay? I hope I can get it all on this slide as I have it. X squared, I lost it. I had it. There it is. X squared minus 5xy plus y cubed is equal to some constant c. Okay? Differential, just an equation. Okay? Two variable equation. All right. Now, let's do, this is your f of xy, that's equal to the c, so let's do what we just said to it. This is your f of x, f of xy, okay? So let's do the partial of that f with respect to x dx plus the partial of that f with respect to y dy, and that's going to have to be 0 because the derivative of that thing is a constant. Okay? What is the partial of f with respect to x? Do you remember that, how to do the partials? 2x minus 5y, and this part has no x dependence, so that's treated as a constant. That's your dx plus, and what's the partial of this f with respect to y? Negative 5x plus 3y squared dy is equal to 0. That's what we've got from doing this thing. Okay. Now, there's a first order differential equation. A lot more complicated than the one we did on the previous page, but there's a first order differential equation. Now, how is that a differential equation? Well, you could move this to the other side here and write that as 5x minus 3y squared dy is equal to this dx. Divide by dx and divide by this thing. There you have a differential equation. dy dx is equal to 2x minus 5y divided by 5x minus 3y squared. It's a differential equation. Really ugly one, you know. It's got a rational expression, really complicated, all tied up. So it's much easier to deal with in differential form, we'll see, than trying to deal with it in a rational expression form. Okay. Now, not too much longer, do we? Huh? 2 minutes. It says not every first order differential equation in differential form, m of xy dx plus n of xy dy equals 0, you're going to be able to solve. Don't even think you could. Not every one of those corresponds to alpha of xy equals c. They just don't. You could have a lot of things there you could make up, and there is no function that way. Okay? So for our purposes, it's more important to turn the foregoing example around, namely, if we're given a first order differential equation, like this one down here, okay, is there some way we can recognize that that one will be a perfect derivative of this? Well, we know it is, but is there some way we can tell that? If there is, then the explicit solution is this thing is equal to c. We know that if we can get back there. Now, do we have time to get the definition done, or is that for next time? What was it? It is, okay. I've got to go, so we'll start next time with definition 2.4.1. We didn't get far enough to have any homework exercises here, so not in this section. So you can do the ones in 2.3. And this, even though it's starting a little shaky, it might seem like, you're going to find out they're not simple, but the steps are fairly simple. So I think you'll find out these go pretty smoothly. Okay? Again, it's the procedure that's more important than the answer. So, well, that's not quite true, but anyway, I've got to run to another class. So, any questions? All right. We'll end this now.